Hello, welcome to episode 7. Today we're going to be talking about numerical solutions to differential equations. So what do I mean by numerical solutions? So suppose we have a very complicated f, ty, right? Suppose this is very complicated and we can't solve it. Or maybe we could solve it through a computer, but it would be very computationally expensive, right? So in those cases, we can approximate and run a calculation. So the way we do this is if we draw a rectangle of solutions, here's our arrows, right? And we're going to have some solution, okay? All we're going to do is essentially cut this up into equally spaced pieces of our time, and over t0 tn. And what we're going to do is we're basically going to take each of these steps is going to be an given by h. So you could use dt if you wanted to, delta t. I'm going to use h because that's the step. So this equation is going to be t0 plus I times h, our step, right? And then what is I? I is a natural number, and it is obviously a natural number, but it is pretty much limited to however many steps you want to take. So we could, if you wanted to take n, if you want to take n steps. So how do we find h? Well, h is going to be t0 minus tn over n. It's going to be sort of the average between these. And we are basically going to say that y of I approximates y of ti with an error ei, right? And I'm actually going to use epsilon here, epsilon I, error, right? So what is it, epsilon I? This epsilon I is equal to the difference between y, ti, so our actual value, and yi. And then obviously the error, so given our initial condition, E0 is, or not E, but epsilon 0 is equal to 0. So that's great, right? Because this is our initial condition when y of t0, right, is going to be equal to y of 0. We're going to be given this t0. So we don't need, so that error is going to be 0 because this is going to be exact. So two sources of error. One is a truncation error, and then the other is round off errors. So we're only going to worry about one of these. When we actually do computations, these errors kind of compound a little bit, but we're going to focus on what we're going to be doing. Actually, I should have mentioned this is actually called Euler's method. Can't believe I forgot to write that down. This is Euler's method for getting numerical solutions. So, how do we do this? Basically, we're gonna assume that the tangent line of the integral curve, right? So this guy, or I'm gonna do another color, brown, is going to approximate that curve, right? So with those little time steps. So we'll use a tangent line equation. So remember, the tangent line is going to be y, so yi plus 1 is equal to y of ty plus f of t y of ti, right? oh yeah, and then this is ti, and then times t minus ti. And obviously we can't calculate this. We cannot calculate this, right? So we gotta have to find, and that's why we're approximating. So we have to approximate these values. So with our identity of ti plus 1 is equal to ti plus h, we can simplify this equation essentially to, so we get t minus ti plus h, this disappears, and we get h f of ti y ti. And once again, since we do not know ti, y ti, we are going to approximate it as, you know, y of I. And so we obviously know our initial conditions y0, so I'm right here, I'm going to write down what this would look like. Y of, well, I'm actually going to write down here, y of I plus 1 is approximately y of I plus h f ti yi, right? That's going to be our approximation. So what does that look like? Y of 1 is equal to y of 0 plus h f of t0 y0. And this is going to be more or less exact, since we know what 0 is. But then we go y of 2 is going to be equal to, well, y of 1 plus h f t1 y1, y of 2 is equal to y of 2, this is actually 3, y of 3 is equal to y of 2 plus h f t2 y2, and then on and on and on and on and on. In a computer program, so this goes all the way up to y of n is equal to y of n minus 1 plus h f of t n minus 1 y n minus 1. Nice. Nice. Right. And so in a computer program, you might think of this if you had a variable for y. We go y plus equals, so you would start y is equal to, you know, our initial y plus h of some function of t and y, and we would go, okay, y plus equals h of f ty, right, of t1. You can kind of think of it like that. Actually, a better way to write this down, let's do this here, as a computer program, would be y equals, so y of t, 0, and then basically for t in t0 to tn, and then here, so let y plus equals h times f of t y, right? So something like that. You'd probably be looking at something like that as a computer program to calculate this. All right. So that's Euler's method, really quickly. And next episode, we're going to look at some more interesting stuff, I think. See you then.